you'll be looking at the correct present predictive connection of CO2 warming and sea level. And I'm also going to start recording this too, so we'll have another record of it that will be available on our website and on YouTube as well. Okay, my background is in physics and electrical engineering. I have a PhD in general engineering and 2 bachelor's and master's in physics. Taught community college for years in physics and electrical technology and computers and microprocessors and also environmental science. So this is the, I would say, outgrowth of my interest in the concern about the environment and the experience of using the textbook, which I have underneath my computer right now, Living in the Environment by Miller, which I used for years teaching community college. So this is a topic that's close to my heart. And especially in this day of global warming, we have a lot to look at. So hopefully you'll see some information that you can take away and act upon. The presentation you're about to see is one that was also already given to the IEEE, which is the Institute for Electrical and Electronic Engineers. That happened in November at Tufts University. And I also gave a similar presentation to another short presentation as well. But it's been published in a number of journals. The longest article, I'll give you the citation for that momentarily, but upcoming is the Journal for Atmospheric Research and also the Advances in Science, Technology, and Engineering Systems Journal, STES, which is an extension of the previous publication of the Society for Implications, Social Implication of Technology. IEEE has their own Society for Social Implications of Technology, and that's where they entertain the environmental implications that we were talking about here. And so that was very well received there. So the important part too is that the basis is my first publication, which happened in October. The 32-pager is an open access paper. It's also available on a tiny URL /ValoneClimate. So that's an easy way to get it. You could click on it right now if you're at your computer, and you can read along, because what I did for the first time in this presentation is to give you all of the main points of this 32-pager, which I never was able to do in a slideshow before, because, for example, for IEEE, I was limited to 20 minutes. And in 20 minutes, you can only show about 20 slides. And so I packed everything in rather quick and finished just up to the wire. But at this point, the same 3 topics of global warming, temperature, ocean height, and atmospheric carbon concentration are covered. So the way I start this presentation is basically to give you a background. And the background is based on my own life. And that is, when I was born right around 1950, within a few months of 1950, I'm surprised at my age, which is almost 70, to look back on this 70 years and say, what the heck has happened to the world? What has happened is something that's never happened before in the history of humankind. And that is, when I was born, only 2.5 billion people were in the world, half of whom were starving. Literally about 1 million people were starving, most in India. And that was a common saying, the starving people in India, don't waste your food. As you grow up in the 50s, that was parental guidance. So this was a true, real problem that was widespread at that time. Have half the population and not enough food. So what I'm also emphasizing besides that is what Norman Borlaug did, and what caused this jump in the rate of growth, which is what the dark brown line shows. The rate of growth started to really accelerate around 1950, 1960. and today we have 7.5 billion. So today the number has tripled, and the effect of the peak of the rate, which went up to 2.1%, and then started decreasing shortly after 1975, was that the growth rate, the growth of population, in other words, the quantity of population, essentially started to decline in its slope slightly, so that in 2020 we're up to this point here, and then we're supposed to level out to around 11 billion or maybe a little bit more around 2100. But the biggest takeaway to this graph is that it takes more than 100 years from the time that the rate of growth peaks to the time when the quantity of this population, whatever the system's population, in this case it's people, will actually start to level out. So keep that in mind as we analyze the Earth situation, especially carbon dioxide. Excuse me. So far, what I'm emphasizing is global population has tripled since 1950. CO2 emissions caused by the same people we're talking about has quadrupled. And the global energy demand, which could be a driver when you think of the CO2, has quintupled, 5 times all in the same period. So this 3, 4, 5 triad, as I call it, is a major impact upon the environment. And the main cause of it, maybe you could look at Dr. Norman Borlaug, Nobel Prize winner, as a savior of mankind back in 1960, who basically went to India, founded the hybrid wheat science. And what's interesting, this video just came out this last month, the man who tried to feed the world with good deeds and unintended consequences. It's amazing that PBS.org is where you can get this, or else on Amazon. I bought 3 of them to give away, DVDs. He's the father of the Green Revolution. And when you teach environmental science, this is exactly what you refer to as an amazing transformation of plenty, the horn of plenty, in other words, seemed to have taken place after 1960. And India hunger was reversed. They started to apply his science of hybridization to other grains and other crops, and found the best and sturdiest and the most disease-resistant ones to then breed, so that they would have a lot more yield per acre, and also be drought resistant as well. So what he told everyone at that time, and this is what I'm trying to share with you guys as well, when you look at the larger picture, which is what he did, he says, I'm giving the world about 20 years. Because he knew that the population was because of the starvation. So he said, okay, let's figure out the food problem, make sure we have plenty of food, but that doesn't necessarily solve the population problem. In fact, it exacerbated it. And so we didn't listen to his warning of 20 years. So now we're getting up to 7.5 billion, headed toward 11. We're facing the same problem again, and we still have a billion people that are starving. That is literally the estimate today in 2020. The number of starving people hasn't changed. It's just there's a lot more people that have benefited from having good food available. So in some ways, this is good news. Hopefully we regard it as an opportunity, because the more people that are available to solve a problem, hopefully we'll solve it more quickly. And the problem can be solved. That's what I'm going to show you, even though there's lots of consternation here that's coming up when you look at the facts of, for example, carbon emissions that have quadrupled since 1950. When you look at the carbon emissions, we're putting out 10 billion, 20 billion, 30 billion, almost 40 billion. We're up to about 37 billion tons of carbon dioxide every single year. Every single year we put up 37 billion tons or more. This graph looks like it's aimed upwards. We've had a little bit of leveling off due to the COVID-19. People aren't burning in fossil fuels and traveling as much, which is a great little respite for about a year. But everyone knows this is going to start shooting up again, because obviously population keeps growing and we're going to overcome the COVID challenge. We won't overcome the global warming challenge, especially if we're going to keep putting carbon that stays in the atmosphere. The 40 gigatons per year, which is what we're headed to, will basically add to the other 410, actually 936 gigatons that are excessively in the air already. But what I want to call your attention to is this rate. Since 1960, this has been recorded by NOAA, and the rate is the amount of CO2 per time. Now, this growth rate has been exceeding 2.7%, not 2.1% where population peaked, but 2.7%. And do you see any chance that this is going to level out? I don't. And if the growth rate isn't leveling out or peaking, then the actual quantity of CO2 has little chance for the next 100 years of leveling out, according to business as usual. We always hope for a big renewable energy influx. All the climatologists say that's all we need, just a little bit of renewable energy, 20, 30, 40, 50% renewables, and everything will level out temperature-wise. Well, I have news for you that the two aren't related, and the gigatons that are already there are the big problem. So let's look at those gigatons. So far, the gigatons are caused by this massive amount of coal, oil, and natural gas. Literally, about 90% of all the world's energy usage is fossil fuel technology. We have a huge carbon footprint that we have to solve. This is number one. And I look at it as number two because it's a long-term problem, at least 100 years before that 90% is going to go down to 10%. But so far, we acknowledge, all the world is acknowledging, especially in Europe, they're acknowledging the fact that they can make a switch to renewable energy within 10, 20, 30 years. And that's a great aspiration to have, and we should have it in the United States as well. Hopefully the next administration will take this and run with it, because all of this needs to be replaced by renewable energy if we have any hope of not having a hothouse Earth. And we're headed toward a hothouse Earth, there's no doubt about it. So let me show you the hothouse problem. And a lot of people I've talked to, I mean, there is a percentage that says, I don't know about carbon dioxide, that the Earth is going through cycles, and they don't really acknowledge the relationship between the carbon dioxide and temperature. Well, here's the experiment from a school teacher. Take 2 soda bottles, both filled half full with water, pop in a little seltzer, Alka-Seltzer, and see the bubbles, carbon dioxide bubbles that formed here. Put the same light on both, and then read the temperature after time. The time we're looking at the bottom here is 20, 40, 60 minutes. Plain water reaches the lower steady state at around 35 degrees from ambient temperature up to about 35. The seltzer water, which is just a little bit extra CO2 added to the air above the water, takes longer to reach the steady state and levels off at 44 degrees, 9 degrees C hotter. And this is a huge amount of temperature, 9 degrees C, you can about double it for Fahrenheit. So far, these numbers haven't sunk in, but maybe they will when we look at the historic record of the Earth. But this, to me, is a dramatic, as he says in his posting of the YouTube video, which you can find this entire video online, very effective, dramatic demo to show the effect of temperature and increased levels of CO2. And it's a heat-trapping gas, in other words. CO2 is the heat-trapping gas that's already in the atmosphere. And that's what I want to show you as far as the correlation. Here is one of the most referred to graphs that we don't see enough of in the daily news to remind people that temperature and CO2 are tightly correlated. Not just loosely correlated, but tightly correlated. Every time we've gone through an ice age, CO2 goes down and temperature goes down. Every time we come out of the ice age, CO2 goes up, temperature goes up. And notice how they track each other. you see 4 ice ages here over 400,000 years. This is a Vostok ice core. It's the most highly referred to ice core that basically then comes up to the present time. And if we view the maximum temperature and maximum CO2 that has ever been reached for 400,000 years, we're at around 290 parts per million. That is the what we climatologists refer to as the starting point or the leveling off point that pre-industrial human race worldwide got used to. We're very comfortable at 290 and the temperature around 15 degrees C, which we call 0 at this point. So that's our references. These are our references. The horizontal lines are reference. Well, from the reference point, we're basically pushing today up to around 410 parts per million. We've gone from 290 to 410 in less than 100 years. That's a 45% increase. 45% increase of a heat-trapping gas, which has never been done on the Earth except for, as you'll see, 50 million years ago. And what do we expect for temperature at this correlated graph? Well, this graph tells us we're going to be into the 6 to 8 degrees C increase range. And it'll probably happen pretty soon. Who knows how soon? By 2100 perhaps? That's soon enough. Well, here's a geological paleoclimatology picture. And if we basically follow the trend, which I already showed you, of the actual CO2 increase, we're looking at the business as usual as A2. And the business as usual graph projects us by 2100 to be around 800 parts per million. We're at 400 now, we're headed up to 800, and 290 is our baseline. So 800 is serious, it is unprecedented in the recent history. However, if we look at the 800 we're headed to for 2100, for A2 business as usual, way up here, we can go back in time, go through our 4 ice ages, and even further, millions of years before that, and guess what? We end up at the Paleocene thermal maximum in the Eocene epoch at 800 parts per million. So it has happened before on the Earth. And the University of Washington, courtesy of, they provide us with this information. Well, here in the Washington, D.C. area at the Smithsonian Museum, Dr. Scott Wing, who I corresponded with about this, gave an entire YouTube lecture. He gave a lecture at Smithsonian, and it's on YouTube. And he basically has this, what I say, museum historian, fossil paleontology approach to the warming that we're headed for. And so he goes back and talks about the Paleocene-Eocene thermal maximum, PETM, and it basically shows that, yep, we went up to around 12 degrees C increase over the reference point that we're talking about. 12 degrees C for 800 parts per million. We're talking about 400 parts per million currently that will drive us up to around 6 degrees. If we double the CO2, we're going to double the temperature. That's what Dr. Wing is telling us, curator of fossil plants. And he does so in such a relaxed point of view, it's almost disturbing. I even corresponded with him saying, you know, shouldn't we be talking more seriously? Shouldn't we be warning the public about how intense and dangerous this is? And he says, well, I just take the larger picture, larger perspective. And talk about larger perspective, here you go. Here is the largest perspective we can ask for. Go back 500 million years. But recently, we're, as I say, pumping up the CO2 in this little ballpark. And if we screech over here to the sea level, this is centigrade, Celsius, then we're still looking to the 0 to 6 degrees. However, notice once again on this graph, the PETM, which we acknowledged was 800 parts per million approximately, is up in the same range of the 12 degree increase. So these are numbers that are beyond shocking, beyond extreme concern. These are crisis situations that are just like COVID, only worse, because it's going to impact the entire world in a long-term effect that you can talk about the overall population effect of migrants, starvation, heat exposure, equatorial region uninhabitable. It's amazing that we don't have a movie to go to about the coming heat hothouse Earth. But I'm sure it'll be soon. Hollywood will catch up. Okay, well, what effect is this having with only a few years? Here you go. Here's the researcher, James Balog, who has done an extreme ice survey of 18 glaciers. And what he found was, for example, the Columbia Glacier is losing 1 mile every 3 years. And this is the 2006 picture of that glacier, Columbia Bay, Alaska. And here's 2012, completely gone. A glacier that disappeared in 6 years. National Geographic covered it. It's basically now historical. You can go back and see the mountains. They were completely covered by the glacier only 6 years ago. And is this happening around the world? Well, yes, actually it is. Antarctica is losing about 100, actually this is 1,500 gigatons in about 10 years. 1,500 gigatons of ice mass have disappeared in Antarctica in approximately 10 years. And when we look at Greenland, surprisingly, it's double that. Greenland doubles the Antarctic ice loss. In the same 10 years, approximately, we're looking at about 3,000, a little bit over 3,000 gigatons of ice mass. Greenland will be melting so fast that we're going to see major changes, not only in the Arctic, which is only going to be a couple decades before that's ice-free. North Arctic is almost ice-free now during the summer, but Greenland is headed to be next. And I always think, well, whoever named Greenland was prophetic, because we're going to see a green land, probably within a few hundred years. And all of that, by the way, as these two melt, just to give you a forewarning, Greenland will contribute to about 10 meters of sea level rise. And you figure it takes 1,000 years or more before Antarctic will melt, that'll contribute, they say, around 70 meters. 60 approximately plus 10 is 70. So we got at least 70 accounted for between these two ice masses of sea level rise in the next, say, 1,000 years or so. But sea level is something I'm not trying to emphasize too much. I got a couple slides on it, but I'm really trying to focus on and convey and communicate the temperature issue. Temperature in CO2, temperature in fossil fuels, temperature in GHG, which is the greenhouse gas forcing. This is a graph showing greenhouse gases and temperature. And once again, you see the graph that, in this case, is looking at the greenhouse gases forcing upwards faster than temperature can follow quickly. So there's a little bit of lag. Luckily, we do have a little bit of a lag. We're up to 1 degree, over 1 degree C change right now. And of course, the greenhouse forcing is seriously leading its way. Well, one of my heroes in life is Dr. Jim Hansen. I've met and talked with him briefly. I get his newsletter. He's written a few books, and he works at New York University, but also he was at NASA Goddard, which is actually here in Beltsville, Maryland. And what he did in 1988, which was unprecedented at the time, was to publish an article and then give senatorial testimony about the coming global warming and climate change. Of course, he was castigated seriously because nobody wanted to believe it. Well, as we look back now, and I published my article in 2019 because of this graph. In 1988, for some reason, he included 2019 as the very last data point on his NASA supercomputer projection of what temperature increase would be experienced worldwide in 2019. Of course, he's got the other years here too. But I was so surprised to see 2019 here. I thought, oh, I got to really celebrate that year. And of course, who in the world, except for Dr. Jim Hansen, would have the audacity to look 30 years in ahead and actually come up with the exact number? Exactly on target. 1.1 degrees is really what we now have seen as an increase from our zero baseline, which is 15 degrees, 15 and a half, approximately C worldwide. So we have to give him great accolades for this accuracy, tremendously accurate compared to anybody else. And he's been reviewed online many times, even previously years ago, saying, oh, he couldn't possibly be right. He won't be anywhere near what's really happening. We're never going to get up to a degree in just a couple of decades. Well, we did, and we're headed up even faster. But there you go with the arrow. Once again, all these different scenarios and reviews, the middle point is where we ended up. And then he also projected into the 2060, and you can extrapolate a little bit more into the 2100. And of course, we're probably looking at the same exact projection, which we see the other experts, even Stanford University, 6 degrees, 46 degrees, which we'll see too. So all the experts are still looking and projecting, even way back from the 1988 point of view, to what CO2 is doing to the world. Well, here's my compilation of Dr. Jim Hansen's publication in 2006. In 2006, what he did is he put in a little innocent, not only the 400,000 year history of temperature and CO2, but he added the sea level information, which is a little bit more difficult to obtain, but he correlated and lined it up with the same max and minimum so that they're all in the same graph. And you end up in 2006, we were only at 377 parts per million. There's our 15 degree, I'm saying average 15 degrees global temperatures, and the NOAA projection, the same kind of information as well. So basically the information can be looked at more closely. We start from 400,000 years. And what I did basically here is to give the skeptics in the audience the chance to look at, and you can review the slideshow later if you like, which one comes first. I've heard criticism that, oh, CO2 has never in history led the temperature rise. Well, yes, it has. If you look at CO2 and just look at any particular vertical line, you'll probably find the black line ahead of the other two lines. And you see that basically anywhere you want. Go through the middle, same thing, and go through the end. Any one of these three will lead the other two. That's what you learn from this graph. It's so remarkable that people haven't, climatologists especially, paleoclimatologists, haven't studied this to the max in order to glean what I found was so easy to glean from the table that Jim Hansen published. Let me step back and explain what did he publish. Well, this table is remarkable. I've never seen a graph that gives us this kind of table. And what you see in between here are dotted lines, horizontal dotted lines. The axes are labeled with 10 parts per million difference, a linear difference, a linear scale for carbon dioxide. We don't have a linear difference for temperature, do we? Yes, we do. Half a degree for every horizontal dotted line. We don't have a linear gradation for sea level, do we? Yes, we do. 10 meters or sea level rise or decrease for every dotted line. So what I'm emphasizing, as I say, is just in this case, temperature, 20 parts per million of CO2. If nothing else you take away, then memorize 1 degree C for 20 parts per million, then just start at 290 and go up to 410, subtract them, you get 120. 290 is our baseline, where we'd love to be and stay. 410 is where we are now. Subtract the 2, you get 120. Divide by this 20 parts per million to find out what type of degree difference will be and trained by that CO2, we get 6 degrees. And that's exactly what I show here. The 6 degree difference is literally driven by the 410. That's it. That's all you can do to analyze the 400,000 years is you come back with a stark realization that all the rhetoric that we see today by literally professors all over the world, UN professors, UN experts, all the IPCC communications and reports, they all miss this point. I'm not sure why, because it's our history. It's our Earth history that we're now examining and easily taking away the relationship. As I point out here, divide by 2, I got 10 parts per million, half a degree, and 10 meters sea level rise. But to me, this is the most serious and egregious problem that we have to deal with immediately. 6 degrees is intolerable. 2 degrees is going to be serious enough. We've seen all kinds of fires and burning of the tundra. This is only going to get worse as we go to 2, 3, 4, and 6 degrees by 2100. That's only 80 years away. So you basically get the impression that the story and the picture is a lot serious than we've been told. The renewable energy conversion is good as a long-term fix, but the short-term fix has to be CO2. What can we do about the CO2 that's in the atmosphere right now? Because, take a look, here's Dr. Solomon, published in the Proceedings of the National Academy of Sciences. She takes the same perspective as Dr. Wing does. Oh, let's look at the long-term paleontology approach that essentially is projected at her point of view. There was only 7 billion tons per year being emitted in the early 2000s. Well, we're up to 37 per year now. So her projection of 4 to 5 degrees C was a little bit underestimated. That's how serious things have become in only 10 years, from 2009 to 2020. 2020. So really, this is 1 degree higher. But look at the difference of her perspective. Well, 2100 is here. You get up to the high temperature. She believes that we're going to stop emitting and somehow just sit there. Maybe that'll be true. That's exactly what this graph says. By 2100, we'll just stop all carbon emissions and stay at 410, which is unlikely. But the point I'm trying to make is that she's going to 3000. For 1,000 years, we're going to stay at 5 degrees more? I wouldn't want to do that. No way. But this is exactly what's published in the journals. And scientists aren't really communicating to the public the seriousness of what they're projecting for the long-term effect of global warming. Here's Stanford University, Brown and Caldera. Brown and Caldera have a wonderful bunch of articles on this. Their projection, once again, is in the 5 degree to 6 degree C range by 2100. So I'm trying to enforce upon the reader, the public, or the viewers that all the climatologists agree on the actual projection by 2100, irrespective of whether renewable energy comes on board or not. If it doesn't, things will only get worse than 6 degrees. We're literally, as you know, from the previous PETM, headed much higher. But say renewable energy does come on board, we can still maintain the 6 degree as the top for 1,000 years. Well, I don't think either scenario is acceptable. And so I want to show you the most extreme revolutionary approach to solving this problem, getting back down to 290. So all this meter sea level rise, threshold of catastrophe, you can find these articles everywhere in the literature of how serious we are. Here's just a little bit of sea level stuff. As a courtesy, I wanted to show you that yes, we are looking at least a couple meters by the end of the century. A couple meters of sea level rise. It's a very slow thing. I hate to say it, but it's like the frog that's sitting in the water that's slowly becoming warmer and warmer. But the red shows us what's happening to the coastline and what will be gone by 2100. All the red stuff will be underwater by 2100, by at least on or below current sea level. So, and here's a projection of what London will look like by 2150. So let me start at the solution stage and kind of look toward the future about what can be done. First of all, we see in the literature the carbon tax has been advocated. And what's surprising is that the carbon tax is actually positive and popular if it's linked to the possibility of funding renewable energy. And that's exactly what we see in the Science Advances report from 2019. Young evangelicals also support it. We see it in the literature. This is the Washington Post 2019. And the question I need to ask is, can we even stabilize the 350 parts per million? 350 is at least a halfway point back down to something that's at least reasonable, even though 2-3 degree change is not necessarily the most comfortable, realizable limit to stay at. But anyways, the important point is the carbon tax idea that could be proposed perhaps by legislation. Well, let me at least throw another phrase at you, and that is negative emissions. Negative emissions is a really revolutionary idea. It basically comes from the carbon sequestration or carbon storage idea. Carbon capture and storage, CCS, is the concept behind this. And there is a free downloadable PDF from nap.edu 10766. And the greenhouse gases that this publication is advocating, the essential lowering of the emissions supposedly will bring us below 2 degree increase. Well, as I say, this misinformation is everywhere in the literature. There's no direct correlation between the two, but it's great to look at the long-term limits on emissions, and of course we need to do both. So this is one approach toward negative emissions. And we see even industrial utility companies looking at this possibility as well. And that's probably a very exciting, interesting approach. Well, one of the things I haven't mentioned yet, except just briefly, the 936 gigatons was the number I threw out at you. And that comes from converting parts per million to gigatons of carbon. And you end up with carbon dioxide. Well, 1 part per million of CO2 equals, worldwide, about 7.8 gigatons of CO2. That's almost 8 gigatons of CO2 just for 1 part per million. So if we're talking about the 120 difference, or in this case, I'm proposing a compromise of 350, so it's only 60 parts per million. 60 times the 7.77 equals about 466 gigatons of CO2. Well, that's a lot. In fact, you'll see another graph where Chevron is talking about and bragging about their 4 megatons per year of carbon capture. Well, that's a drop in the bucket. They've got to go 1,000 times more before they're even into the gigaton range. 1,000 times 4 megatons will give you 4 gigatons. And then they still got to go 100 more to get into 400 gigatons. So this is a very challenging number that really requires a global carbon reduction program, exactly like we've experienced with COVID, only more seriously financially committed to, because the whole world is going to have to start doing this in a major gigaton capture mode in order to just stabilize our Earth's CO2 level to 350. So our temperature capture will start leveling out. And that's what we want. We want the temperature to finally level out and not keep increasing. And then, so how do we do it? Well, If we basically are adding 40 gigatons per year, that means we have to exceed the capture rate by at least say 50 to 100. So I'm stretching it and saying we should go for 100 gigatons for 10 years. And of course, then you get to 1,000 gigatons, which will take care of everything. But even if we go for 5 years and then 50 gigatons after that, we basically can stabilize the atmospheric levels as we work on renewable energy and implementation. And as lots of different publications state, pulling CO2 out of the air and using it can be and will be $1 trillion business. And I want to emphasize the fact that as we saw those climate change 400,000 year graphs, it is reversible. All of those CO2, temperature, and sea level things that were going up together also went down together. So all we have to do is change one of the variables and the other two will go down as well. And the way to do it really is to reduce the CO2 in the atmosphere, bring that down. So it's no longer trapping heat. And people are doing that. This is NCSU, University, North Carolina, that's developed a polymer with successive layers that can trap and absorb CO2. Journal article on that. We also published Future Energy E-News. You can subscribe to Future Energy E-News on our website, integrityresearchinstitute.org, and just scroll down the right-hand side and punch in your email. And Constant Contact needs you to do it personally in order to get our free email every month. We cover basically 5 stories that are on emerging energy, propulsion, and bioenergetics every year. And we already did cover that capturing thing. So here we get to a more serious, Jewel magazine, by the way, is very popular for these type of environmental solutions. 2018, here's a process by David Keith that essentially looks at the capturing CO2 in a large volume mode. And the costs right now are at least $100 per ton. We're basically looking at $10 per ton for a new novel approach by Project Vesta. But the ideal would be $1 a ton. But even at $1 a ton, if we're trying to do 50 gigatons a year, we're basically committing $50 billion. And this could be, if it's $10, $500 billion every year, just to grab the 50 gigatons out of the air. That's already almost 50 gigatons will be going up shortly as we surpass the 40. So we really should be aiming at twice that much. In other words, $1 trillion business, as we already saw was projected. Carbon Engineering is another company, which I'll show you another picture of, who's doing this on a big, large scale. High Tech is another company that's essentially looking at making hydrogen out of their smog and various fossil fuel emissions. Onboard electrolyzers also are being implemented and experimented with to make hydrogen. And there's novel methods for making hydrogen that are actually very worthwhile in this approach. Carbon Engineering out of Calgary, Canada is the only one I've seen with this kind of scenario. I mean, this is really impressive. for an artist even to propose the fact that, yes, we're going to start treating the atmosphere in a really big way. Gigatons are now possible when you have this kind of hardware. And of course, this needs to be publicly funded for direct air capture for CCU and CCS. Carbon capture utilization, but more importantly and more valuable is carbon capture and storage. I have to mention the trillion tree solution that I've heard bantered around. Trillion trees are nice. They take decades to grow before they even get up to the 1 ton per tree that trees normally sequester. However, when you cut them down and burn them, all that goes back up in the air. So trees are a short-term storage medium, even if we go ahead with the trillion tree idea to temporarily over the next 100 years store 1 trillion tons of CO2, which would be great. I mean, we get that 936 gigatons out of the air, perhaps. But the important part is all those trees would have to stay living, but they don't. They basically die, fall over, and all the carbon goes back into the atmosphere. So overall, let's look at more serious approaches that capture carbon into rocks. And this, to me, is the most exciting and probably the most progressive gigaton CCS I've ever found. ProjectVesta.org, nonprofit, they found a green olivine rock. It's a sandy substance that can actually speed up the carbon capture, and it also deacidifies the oceans. So it's a volcanic mineral. And they found that as it weathers, it will start grabbing CO2. So their current, you'll see on their website, their current project is to experiment with this basically on a sea bed, on a seashore. And, and MIT Technology Review and many other journals have published Earth Systems Dynamics and so forth, the benefits of it. In my last few slides, simply show you other approaches. For example, as you prepare for the next several decades of heat increase, which will get hotter and hotter before it starts to get cooler as gigatons finally get sequestered. In the meantime, everyone should be using white on surfaces like flat roofs, and also on pavements, and also on your tilted roof. And for insulation, there's a much better insulation than the fiberglass stuff you buy at the hardware store. It's phase change insulation. If you look for phase change insulation anywhere on the internet, Install Corp is one of them. There's many other companies that do sell them, and they sell them for different ranges. And they basically capture 10 to 100 times better BTUs and insulate and keep the indoor temperature at whatever you want. For example, for warehouses, you might be able to tolerate the 77, 84 Fahrenheit, but for indoor air, it'd be great to store it. And as I say, you can pick the insulation, phase change insulation that will stabilize the indoor temperature. So it's quite exciting that phase change insulation can be used on the attic insulation across. I talked to the president of that Install Corp, by the way, and he essentially said that he was able to, for a warehouse, literally prevent them from installing air conditioning. And instead, he had just installed phase change insulation across the top. That's how powerful this stuff is. And the last thing I should say, temperature indoors only goes up and down 2 degrees when you do this correctly, even though outdoor temperature could be 80, 90 degrees. And in regards to worldwide renewable energy, this is probably one of the more exciting proposals. 100% renewable in 139 countries. He has YouTube videos explaining it. Mark Jacobson is the name that you need to Google to see this wonderful video. He has several videos. By 2050, he says 139 countries that he names can all switch to renewable, and he shows how it will create jobs and also, of course, get rid of the fossil fuel problem and emissions problem, which is my main concern. So there's my article. You can download it for free, tinyurl/TheLoneClimate. And hopefully, if you pass out this article, pass the website link to other people, try to let your congressman know that this is a serious issue that needs to be addressed. And the way to address it is by carbon capture. This information and the solution, gigaton carbon capture, has not been popularized or promoted or advertised at all, but we certainly need it in order to finally solve the problem once and for all. So I think we're at the 10-minute break time, and so if you do have any other questions, feel free to email me, but at this point it looks like I'll probably move on to going for our break, and however, I guess we do have our lunch break coming up, so maybe we can forego the 10-minute line. And let me see what I can see here. Princeton University says that CO2 is irrelevant. Yeah, that's a problem. Experts look at methane, for example. There's another question about methane. Well, we can look at methane all you want, And if you do the numbers, you'll find that methane has about literally 5% effect on temperature. Even if you're looking at the whole tundra releasing tons of methane that it will do and is doing now, it's still a small drop in the bucket compared to the atmospheric 40 gigatons going up every year. CO2 is a heat trapping gas, and is the major impact is from the CO2 that we're emitting. So this is basically the issue that is happening. Of course, there are nice agricultural solutions. I see some questions about our agricultural effects. Um, the video, The Man Who Tried to Feed the World, is available on the pbs.org website. I highly recommend it for people to consider looking at the history of our last century, and basically the ancient grains and um, fuel that's required for creating biofuel. Biofuel is definitely a controversial subject. Biofuels seem to be great, especially when they're developed by renewable energy. Essentially, if we're capturing CO2 to create the biofuel and then releasing it, it's carbon neutral. So essentially, it's great to see the transition, but our institute hopes for and is aiming for the electrical type of energy propulsion, and even electric clothes and electrification for electrotherapy. It's amazing how all three program areas find benefits from electricity. And of course, I should end with the surprising insight into electrons. And of course, we'll have other people talking about electrons, such as Bill Alec tomorrow, the secrets of electrons and electron spin. But I thought I'd leave you with a little bit of a joke. Years ago, they claimed that Edison came up with an idea about selling electrons to the public. And he developed utilities, and they charge money for buying so many electrons every month from an electric utility. However, the agreement that you have to sign with the utility is that if after you buy the so many electrons, you have to give them back to the utility so they can resell them back to you next month, which is actually a very true scientific fact. But it's surprising that the electron not only has an infinite, almost eternal lifespan, it doesn't decay, but also it has to be recycled as well, just like the proton, interestingly enough. So I thank you for your attention, and let's take an hour break time for lunch, and then we'll come back at 2 p.m. Eastern time for the presentation, live presentation by Mike Campbell. So thanks again.